going on. But I know we're all here for a really special presentation this evening, so I'd like to say a few words and get us started. So my name is Rachel, and I'm here as part of Science at Cal. First of all, can you hear me in the back? It's a great honor for me to introduce our speaker, Professor Carlo H. Sequin, who has been a wonderful and generous supporter of Science at Cal over the years, presenting talks and being a part of creative panel discussions and connecting with us on our exploration of where art and science and research intersect. So I want to say some things about Professor Sequin. He followed a rather adventurous path leading to his faculty appointment at UC Berkeley. After receiving his PhD in experimental physics from the University of Basel, Switzerland, in 1969, his work at the Institute of Applied Physics in Basel concerned interface physics of MOS, metal oxide silicon, I looked it up, transistors, and problems of applied electronics in the field of cybernetic models. So from there, he moved on to Bell Telephone Laboratories in Murray Hill, New Jersey, where he worked on the design and investigation of charge-coupled devices for imaging and signal processing applications. And at Bell Labs, he also got introduced to the world of computer graphics in classes with the also renowned Ken Knowlton. In 1977, I'm happy to say he joined the faculty of the Electrical Engineering and Computer Science Department at UC Berkeley. He started out by teaching courses on the subject of very large-scale VLSI integrated circuits, thereby trying to build a bridge between the computer science division and the electrical engineering faculty. And then in the early 1980s, jointly with David Patterson, he introduced RISC, the RISC concept to the world of microcomputers. He was head of the computer science division from 1980 to 1983. Dr. Sequin is a fellow of the Association for Computing Machinery, a fellow of the Institute of Electrical and Electronics Engineers, and he has been elected to the Swiss Academy of Engineering Sciences. So in addition to these professional credentials, Carlo Sequin is an artist, a sculptor, who translates what he thinks about scientifically into incredible works of art. And I'm going to close my introduction now by quoting his own words. When creating abstract sculptures, I see myself as a composer in the realm of pure geometry. The artistic achievement then lies in finding a procedural formulation that can reflect the inherent symmetries and constructive elegance that seems to lie beneath many sculptural masterpieces, as well as at the foundations of the physical laws of our universe. With that, please join me in welcoming Professor Carlo.
Wow, thank you. Where did you find those words? Well, thank you very much, Rachel. Hard act to follow now. So, that's the official title. And I hope very much that when you heard about this talk, you did not come with the wrong expectations. Because talk is not about pictures like this, and not like this either. No. This is about sculptures made from knots, or using mathematical knots as constructive sculptural building blocks. And you may wonder, how does anybody get interested in a subject like that? Well, I guess it has to do with my upbringing. I grew up in Basel, Switzerland, where I attended the Mathematisch-Naturwissenschaftliche Gymnasium. This is a high school with emphasis on mathematics and science. During my years at the university, I heard most of my mathematics lectures in this 500-year-old building, where many famous mathematicians have lectured, such as Jacob Bernoulli or Leonhard Euler. And from a early age on, I was fascinated with numbers. Then during high school, I fell in love with geometry. In 11th grade, we had a subject called descriptive geometry, where we constructed the intersection lines between two cones or two cylinders, and I thought that was really cool stuff. So ever since, geometry has been in my bloodstream, and it has never left me. In most of my professional assignments, therefore, during the last 50 years, I always looked for the geometry component. This was true in my first job at Bell Labs in Murray Hill, where we focused on the layout of the charge-coupled image sensors, which then eventually led to the very first solid-state television camera. And this success is really what then got me to Berkeley, where I teamed up with David Patterson, and we built the first reduced instruction set computer on a chip, essentially arguing that sometimes a simpler instruction set, but going very fast, is much more powerful than a very elaborate instruction set with hundreds of different instructions. Because of that work on the layout of the RISC chip, my students and I focused on programs that would actually generate these kind of layouts, because as we get from 1,000 to 10,000 to 1,000,000 transistors, you cannot do that by hand anymore. So there are plenty of 2D geometry programs. We then needed a new home for computer science, and my interest transformed from two-dimensional geometry to three-dimensional geometry, and I helped a lot in the design of a soda hall, which you see at top right. Later, I teamed up with Paul Wright in mechanical engineering, and we developed optimized tool paths for 3-axis milling machines, so we could make these free-form surfaces like this three-dimensional yin-yang thing that you see depicted here. And then came along 3D printers. During the last 2 decades, I have now worked mostly with artists and with mathematicians, and the top row shows some of the mathematical visualization models which were fabricated on 3D printers. The bottom row shows 2 larger sculptures that emerged from my collaboration with Brent Collins. All of these involve some intricate geometry, but tonight I will focus specifically on mathematical knots. First of all, this is not a mathematical knot. Mathematical knots must be closed loops of string. So once that loop is closed, you cannot change the mathematical knot except by cutting the string again. All simple mathematical knots are well known and have been tabulated. Here is the beginning of the so-called knot table. The table is organized by the minimal number of possible crossings that will show if you try to draw this knot on a piece of paper. Knot 3 sub 0, the simplest one, is the mathematical knot, or the name for the trefoil knot. 4 sub 1 is known as the figure-8 knot. And then there are 2 different knots with just 5 crossings, and they cannot be turned into one another. They're really different. There are 3 knots with 6 crossings, 7 knots with 7 crossings, and so on. Here is a complex knot with 10 crossings. Most of these complex knots have very little symmetry, but I would like to find the ones with the highest degree of symmetry possible. Now, what does that mean? So here is a brief introduction to the concept of symmetry in a more general sense than you might know it. An object is symmetric if there exists a transformation such as mirroring or rotation or translation, which actually maps the object back onto itself so it looks the same. The more ways in which we can do this, the more symmetry that particular object has. Here tonight we will mostly deal with the following 3 types of symmetry. The best known is mirror symmetry. It provides 2 ways of mapping a scene back onto itself. First, as is, that means a do nothing operation, and then second, mirroring the object and pasting it back onto itself. Next we have the cyclic or rotational symmetry. In the middle example, that thing has 3-fold rotational symmetry, because there are 3 angles of rotation that we can apply to this disk, and it always looks the same. Finally, there are the dihedral objects, which have both rotational and mirror symmetry. The example on the right has an 8-fold rotational symmetry, but in each one of those 8 rotational positions, you can also optionally mirror the object. So there is a total of 16 different ways that this object maps back onto itself. So I'm looking for kind of knot configurations that have many of these ways of being transformed and the map back onto itself. For a few semesters, I've been running a project labeled The Beauty of Knots, and the participating undergraduate students were encouraged to pick a simple knot from the knot table and to turn it into some nice little 3D sculpture. Some unassuming knots turned out to have some hidden symmetry, and the students often exploited that symmetry because we have a feeling that symmetrical things are inherently beautiful. Here is the example of knot 5 sub 2. The diagram in the knot table already hints at a possible 2-fold rotational axis marked with the red line. This would be a C2 symmetry axis, so it's cyclic rotation and it has 2 clicks to make a full turn. This particular sculpture shown here actually maintains that 2-fold rotational symmetry, although the position of the various lobes have been placed quite differently from what you see in the diagram. For the knot 6 sub 1, the diagram in the table does not immediately imply any symmetry, but by playing with string or with pipe cleaners, one quickly finds that it also has this C2 rotational symmetry, which has been exploited again in this particular sculpture. Here's the second simplest knot in the table, the figure-8 knot. It has a somewhat more complicated form of symmetry that also combines rotation and mirroring. In this case, we can map this sculpture back onto itself by rotating it through 90 degrees and simultaneously mirroring it upside down. And we can do that 4 times, so it has a total of 4 ways of mapping back to itself. And this particular glide symmetry is denoted with the symbol S4. And we'll see that again later. The other notable thing about this sculpture is that it is in bronze. And I have to thank Steve Reinmuth for this. Steve Reinmuth runs a bronze studio in Eugene, Oregon. He can turn my plastic models into small bronze sculptures using an investment casting process. He has figured out how to use the PLA and ABS models that come off the inexpensive 3D printers, just like the wax originals in the classical investment casting process. He dips the 3D prints repeatedly into a bath of plaster slurry to form a thick ceramic shell. Then he puts them in a kiln, and for these plastic sculptures he has to increase the temperature carefully by an extra 200 degrees, but then the plastic will sublimate into gas without leaving any trace. And so it leaves a nice little hollow in the plaster shell. And then you can come and pour liquid bronze into it. When everything has cooled down, Steve Reinmuth breaks away the ceramic shell and cleans and polishes the metal sculptures, and then provides them with a nice little patina that use a clever combination of chemistry and heat applied with a flame torch. Here is another beautiful example of his craftsmanship. So the fabrication part is taken off nicely with Steve Reinmuth, and I can really concentrate on the design issues. This particular knot shows up in the table as 940. And the diagram in the knot table may possibly hint at some 2-fold rotational axis that we have seen before. But it turns out that this knot is also known as the Chinese button knot. When implemented with a thick cord and pulled tight, it forms a nice spherical cluster that may serve as a button in some of the Chinese garments. It may also exhibit perfect six-fold so-called D3 dihedral symmetry with rotation 3 and a mirroring option. This is difficult to see in the knot diagram. And in general, the mathematical knot tables are really not much help for determining the maximal symmetry of a particular knot. Here are all 21 possible knots with exactly 8 crossings. And here are all the 49 knots that have exactly 9 crossings. They are represented by these flat, uninspiring 2.5 dimensional images. The figures seem to get ever more convoluted as we get to more crossings, and it gets ever more difficult to find ones with high symmetry.
Carlo, why was there a red line with a question mark on the left of the previous slide? Yeah, that one.
Well, because it sort of implies, though there might be a twofold rotational symmetry. And yes, you can actually force that and create a representation of that knot that indeed has this twofold axis. But you know, it's not immediately clear. You have to really kind of play with this knot and figure it out. The moment that I discovered that it actually has a threefold rotational symmetries, well then, you know, who cares about the twofold rotational symmetry? Particularly if in the D3 symmetry, you get 3 clicks of rotation around the z-axis. And for each one of those, you get also a mirroring by flipping it upside down. So I get, in addition to the threefold axis, I get 3 more axes that are C2 axes. So, while it is quite difficult for a given knot to find out what its highest symmetry may be, it is easier to use some procedural approach and create something that has some desired symmetry, and then push it in some way to make sure that it actually is a mathematical knot. Now tonight there are 5 different approaches to do this that I want to briefly discuss. The first one starts with a simple torus knot. Torus knots are highly structured symmetrical knots. They are obtained by winding a thread around a donut in a very even-handed helical manner. The example here on the top is the torus knot 5, 2. It dives 5 times through the hole in the middle, and it has 5-fold rotational symmetry. And then the 2 indicates that it does this while the cord travels twice around the central symmetry axis. Below are several other simple torus knots. The simplest one is torus knot 3, 2 on the very left, which you have already seen is the trefoil knot. And now let's look a little closer at the one on the very right, which is labeled as 5, 3 torus knot. And it turns out that torus knots 5, 3 and 3, 5 are actually topologically the same one. So you can take a string and form one or the other, okay? But they look quite differently when you actually see them wound around a bagel or something like that. Now, when you make a sculpture, the topology is one thing, but the really important thing, of course, is to deal with the geometry. And here in this poster sculpture for tonight's talk, we have this knot, which is 3, 5, the torus knot. But you can see I deviated from the strictly kind of helical or circular lobes and gave them a more triangular shape to make it more interesting. In addition, anytime the filament dives through the middle, I kind of narrowed down the cross section. So it has this variation like breathing from thick to thin and then thick again. And finally, I didn't just use a circle that sweeps along this particular knot curve, but I used sort of a crescent shape. Yeah, and all of that sort of combines to, I think, something that is a much more interesting looking sculpture than the plain old 3, 5 torus knot. Now what about making knots that have a much higher degree of symmetry? Well, of course, we can just pick a suitable torus knot. There are infinitely many of these torus knots. They all have rotational symmetry given by that first index, and that index can be arbitrarily high. I can make it 257 if I like. But those sculptures will not look very interesting. They're too even, too regular, boring, and they may look more like, a cooling coil in a power plant than a, actual sculpture. Nevertheless, these Torus knots provide a good starting point for making other interesting knot sculptures. Let's start again with knot 3,5 and kind of squish it flat. Right, so here was a nice rounded Torus knot, and then I kind of did this on the computer. If you push it all the way until it gets completely flat, you get this stencil on the right, okay? And of course now it has all these intersections. But that's where the new freedom comes in. The 12 points marked with red dots, I can choose who goes over and who goes under. And as I choose this in different ways, I get actually different sculptures. So the simplest way to make something interesting is to have a strictly alternating knot. That means as you follow along the strand, you go over and then under and then over and under and repeat that strictly all the way around. Here are two simple examples that shows that the knot actually changes when you go from a simple Torus knot to one of these alternating knots. Above the two images in yellow, I list the original Torus knot that I started from, and then below the images, I list the modified alternating versions of these knots. On the left, the figure-8 knot emerges again, and on the right, you can see again the Chinese button knot that I've introduced earlier. In general, these vortex knots have a number of crossings that is given by the product of S and T, the symmetry of the knot and the number of turns -1 as it loops around. These special braids are also quite popular with cowboys. Cowboys call these kinds of braids Turk's head knots. They're often used to make something pretty and useful in conjunction with horses. Here are two close-up views made from rawhide, which are strips cut from the hide of a cow, or from latigo leather, which are colored strips of tanned hide infused with some oils and waxes. Cowboys have their own language to talk about these Turk's head knots. They see them as braids that follow around in a cylindrical ring. And they have two parameters. P, the number of parts, tell how many strands you would sever if you cut through that braid at the right angle. And I call this turns. And then B, the number of bites or bays, and that shows how many of these rounded scallop hoops you get as you go once around the edge. And that is the one that I indicated with S because it also defines what rotational symmetry this cylindrical braid would have. In the purest form, this knot is woven from one single filament or thong that closes on itself, and this happens only when P and B are mutually prime. You have no common factor. So, yeah, question?
Just a quick question. Now, symmetry, that's just not a 1 or a 0, is it? It's not just...
No, symmetry comes in these families that I mentioned before, mirror symmetry, rotational symmetry, and when you ever have, say, rotational symmetry, there's always this index that says, how many clicks does it take to make a full turn? So a C3 would get 3 different rotations that always look the same. So there's definitely more information than just it's symmetric or not. You have to say what class it is. What's that?
What's the scale of symmetry? It goes from 0 to blank?
No, that's not it either. You really have to pick what mechanism you use to map this thing back onto itself, so what family, and then some of these families have a number attached with it that says how many clicks you make for a full rotation. So to just repeat quickly, the transformation that we've done is we started with a Torus knot, squashed it flat, and we got this template for this flat braid. And then we can turn this into an alternating knot by doing strictly up, down, up, down. And that's what you see at the bottom left in yellow. And I have a model here I can sort of pass around. Okay. Now we can take this flat ribbon and turn it like a smoke ring kind of through itself by 90 degrees, which essentially puts that braid on edge. And now you get these cylindrical kind of Turk's head knots, and I follow the yellow one with the red one. And now we do one more step. We take this kind of cylindrical braid and I shrink wrap it around a sphere. Okay. And on the lower right you see the result, and I call this a ball knot, because many sculptures, such as the Incas for instance, they have such ball knots which they have woven from either reeds or from vines. And then they use them to actually play ball with them. Here is a whole collection of these ball knots, mapping different braids in different ways into different styles of these ball knots. The first parameter again indicates the order of the rotational vertical symmetry axis, and the second parameter simply tells you how many times the filament actually travels around the central symmetry axis. Okay, but there are different ways of generating symmetrical objects that may be knots. Another approach to make symmetrical knots starts out with a nice regular polyhedron, such as a cube or a prism or maybe a tetrahedron. Now, on this tetrahedron, I want to run the filament in such a way that it follows every edge exactly once. This would then be called an Eulerian circuit. Okay? But this is only possible if at all the corners there is an even number of edges coming together, so that whenever you enter that corner, you can also still have a row to exit. Now this is not good for the tetrahedron because all the vertices are valence 3. So in order to get them to an even valence, what I do, I will take the top and the bottom edges shown in faint white here, and I duplicate them. So now every vertex has essentially 4 edges coming together. Yes, please.
Sorry, what's a valence?
Valence is the number of edges that come together at the point. So valence 3, valence 4, valence 5. Okay, so we have fixed that. And now I can actually make an Eulerian circuit. And for instance, you can see this on this graph. If you start at the arrow and first follow the green legs, and then the orange ones, and then magenta, and then blue, and you're back at the same starting point. And you have traveled through all of the edges exactly once. Now, to make this more interesting, on the doubled edges, I just don't run the strands parallel to itself, but I actually take those 2 strands and I twist them around each other, and that makes this more interesting. On the right, you see a pipe cleaner model, so small little models that I typically make in order to kind of figure out whether the idea has any merit. And then here is the actual 3D print that goes with that. Yes?
It looks like we've crossed the upper edge and the lower edge twice, not once.
Yes, because I duplicated the edges. That was my trick, because these vertices in the tetrahedron with the white edge, they would be valence 3. I need to have as many inputs as outputs to this point, so I have to make them valence 4. So this is no longer tetrahedron because I duplicated these edges deliberately for the purpose that I can run essentially along that edge twice. But then in addition, I take those 2 filaments and I twist them around each other.
So is that a modified Eulerian cycle?
Well, it's a Eulerian cycle on a modified graph, because the graph is no longer a tetrahedron. It's something more complicated, you know. But I have to do that, otherwise I get stuck the second time I hit one of these vertices. There's no way out, right? Okay, so this particular thing has, again, this interesting S4 symmetry. I remind you, that's like turn 90 degree, flip upside down. Turn another 90 degree, flip upside down. And by 4 times, you're back where you kind of started. Now, it depends really how you twist those wire strands around each other. If we take all of the helices that we have and we turn them the same way, then we will not obtain the S4 symmetry, but now we have the green solution. And that one has only D2 symmetry, a two-fold rotational axis with sort of a flip upside down. You also notice that this knot is no longer alternating, while on the white one you strictly go under and then over and then under and over. This one here, you basically go over and then over again, okay? And it turns out, when you really play with that with pipe cleaner, it's not even an 8-crossing knot anymore. It actually turns out you can deform it, and so you find a projection that has only 7 crossings. And then if you look in the table, look hard enough, you find out, yes, that's actually knot 7 sub 4. How did I figure this out? As I said before, you make a model with pipe cleaners and you play around with it, and then suddenly you can see what is going on. Okay, very quickly, I can do the same trick kind of with a cube. Again, all the vertices are valence 3. I need to duplicate a few of the edges to make them all valence 4. And so I duplicate the upper 2 edges here, I duplicate the lower 2 edges, and now every one of these vertices in the graph has 4 roads coming in or out. And again, I do some twisting on these edges that I run the filament through twice. And you can see the result on the right. And again, I've shown the more interesting symmetry solution first. Again, we get this S4 symmetry. And again, I can play around with the twists. And if I change the twist of one of these pairs from what it was before, then it has only D2 symmetry rather than S4 symmetry. And it still is a 12-crossing knot, so it's not like in the previous case where it kind of got degraded to a lesser knot. It still has a full 12 crossings, even under the best way of manipulating it. And last but not least, I started with a semi-regular cube octahedron. It has 6 square faces and it has 8 triangular faces, but fortunately all the vertices are already valence 4. So it is not hard to find an Euler path visiting all edges exactly once. Here I made the knots more interesting by twisting the 2 strands that go through one and the same vertex around each other a couple of times. Okay? Now I can shoot either for maximal symmetry, as shown in the green case, and make all the helices the same, but then it turns out this is no longer a single knot. It actually turns out to be 4 separate interlinked loops. And you can find that if it grabs of 2 opposite edges, it looks fairly rigid, but if you grab 2 other ones, you can see it kind of rattles. And if you carefully follow with your finger one of these lines, you see it kind of travels around, and there are 4 of these interwoven into one another. If I really want to have a single knot, a single loop, I must break that symmetry somehow. And so in this case, I had to introduce 3 of these coils that have an extra half twist. And so it looks like, you know, there are 4 here, but there are only 3 there. So it's less symmetrical than the other one, but now this is one single knot. Okay, number 3. The third approach uses simple knots as building blocks. Here I start again with a tetrahedron, but now I place 4 separate trefoils on each one of its faces. I let them extend beyond the edges in such a way that neighboring loops can actually interlock with one another. And if I simply were to form this and print it that way, it would be a rather loose and rattly kind of, assembly. But I can then thicken those strands and until they really block one another. And if they're fattened enough, you get sort of a shape like that, and now that really keeps its shape, even though it's composed out of 4 separate trefoils. Now in these figures you cannot really see that it's 4 separate trefoil, so let me show you the 4 trefoils properly colored in. It's 4 different colors, and now you can really see what's going on and how these things are interlinked with one another. it turns out you can make more complex interlinking. So for instance here, I still have 4 trefoils, but now they interlink kind of twice, with their neighbors, and that makes it a more sort of complicated link. This particular shape shown in just all the same color, but from 2 different sides. On the left, you're basically facing one of these trefoils going like that, here and then again, okay? And then on the other one, you see that same thing from behind, and you're kind of looking into a void between 3 separate trefoils. And of course, what works for the tetrahedron can also work for the other regular solids that are made from triangles, the octahedron or the icosahedron, which has 20 triangles. Let's jump directly to the icosahedron. Now we have 20 trefoils placed on each of the 20 triangles. And again, we stick them over the edge so they can interlink with their neighbors. And this one shows the simpler linking, where you have just exactly one link with a neighbor. But again, I can make this more complicated if I want to. And now, in this one, every one of the trefoils interlinks with a neighbor twice. Okay? And I point out with the 2 arrows, 2 of these crossings between the same pair of trefoils shown in orange and shown in green. And then you can actually create that thing. And here it is, in metal. It's called the Arabic icosahedron because it reminds me of what you see in some of the Moorish patterns in the windows of the Alhambra in Spain. What about the dodecahedron? Well, this now has pentagons, but I can make pentafoils. I can make some 5-lobed little knots and then put 12 of them together. And if you do that, you get this one, and this is also in metal, so watch out, a little bit heavy there. How do you build a thing like that? I mean, it seems like no milling machine can go to the inside and mill this thing out. You can't make a mold of that thing because you couldn't go and have the inner part and how to remove it. So how was this thing created? Well, it's a special process of layered manufacturing. It's yet just another 3D printing process that was actually coming online about around the year 2000, introduced by a company, Pro Metal, which is a subsidiary of X1 Corporation. So this printing process starts out with putting down layers of stainless steel powder and then dribbling in selectively a very proprietary binder and doing this layer by layer by layer. And then when you're all done, you blow away all the powder that has not been bound together. And so now you have your sculpture basically as a green part, as they call it, which is stainless steel particles held together with a binder. You put that in a kiln and you raise the temperature to the point where the stainless steel particles start to fuse together. So you already see that's a special binder that can take this temperature where this happens. But even more, now you want to get rid of the binder. So now as you increase the temperature further, before the stainless steel starts to get all soggy and kind of drift away, the binder has to kind of dissolve and run out, okay? And once they discover the binder, they don't tell you how they do it because that would lose them their customers, right? But once the binder is gone, you don't really have a solid steel sculpture. You only have a porous sculpture that has a lot of voids in there. Now you take this thing and you dip it in liquid bronze. And by capillary action, the bronze goes into all the little holes, and the final sculpture that is passing around here is essentially 50% stainless steel, 50% bronze. And today, you can readily get yourself something made like that through an online service like Shapeways. You send them a file, they send you a quote, you say yes, you send them a credit card number, and a week later, you get a part like that. It's wonderful stuff. Now, it's typically 20 times as expensive as doing it in plastic, right? So in plastic, a thing like that, Shapeway may charge you like $500, okay? I think this one cost me $600, and that was a while ago. It's probably more now. Okay, number 4. We start with a knot of modest complexity, but then we can increase that complexity by splitting the filament lengthwise. You probably know that if you take a twisted Mobius band and you cut it lengthwise down the middle, what happens? It kind of opens up into a loop that's twice as long. So it's still, a single loop, okay, but twice as long. And on the left here, you can see MC Escher essentially has done that. He started with the trivial knot or the single loop unknot, but he followed this with a triply twisted Mobius band. And then when you split that down the middle, then you can see what results is actually a trefoil knot. Great, okay. So we have a trefoil knot. Now, could I run a band along that trefoil knot and also triply twist it and then cut it lengthwise? And yes, you can. And that's what results. So you can clearly see kind of the trefoil, but then it's kind of split. And because inherently this ribbon that I started out with twists 3 times through 180 degrees, when you go once around the full loop, you essentially come from this strand to the other strand. And then you make a second loop and come back to the first strand again. Okay? So it's a single knot again. But now the trefoil had 3 crossings. This now has 15 crossings. Okay? 4 in each one of the clusters and then 1 out there where it kind of flips over itself. Now, this particular concept and design has been used in the year 2005 at the annual Snow Sculpting Championship in Breckenridge, Colorado. So we actually built this thing in 5 days. It was 12 feet tall, okay? It was pretty cold, and every day we were kind of rasping away from this big block of snow that they give you, which is 10 by 10 by 12 feet tall. And then here it was, and its name was obviously Not Divided. Okay, and of course, intended double meaning. Finally, the last approach uses a recursive procedure where a process is repeatedly applied to its own results. Okay? For instance, we can replace every simple crossing of 2 strands that we have in a given knot, and at that place, put a whole simple knot by itself. Or more generally, we can take a very small, simple piece of a knot and replace it with a more complex geometry. Let me start with a simple 2D example. You're probably familiar with the Hilbert curve, which is one of those so-called space-filling curves. Okay? We start out with a simple kind of square or U shape, and then at every corner, at every elbow, we replace that shape with this somewhat more complicated shape. And of course, this more complicated shape has again little elbows. And at each one of these elbows, we put again a scaled down version at this particular place. And we can repeat that on this slide. I think I repeated it 6 times. And you can see by 6 times, we already have a very dense kind of coverage of that particular plane. You do that 2 or 3 more times, you couldn't see kind of any white space anymore. And of course, conceptually, you have to go through infinity to really fill the plane. So I showed this to my students in a graduate class, and I simply said, your homework, do this in 3D. Okay. Well, I guess they were trained enough to figure out fairly quickly, well, it was a square before, now it's a cube, okay? And in this cube, we may be starting out with what's called a Hamiltonian path, which visits all the 8 vertices of a cube exactly once, but then we break open one of these legs and kind of twist them in this particular way. So you can see from input to output, sort of, this is like an elbow. So now we can take this particular shape and scale it down by a factor of 2, and then place one of these scaled down shapes at every location where we have one of these little elbows in the proper orientation. And what you get is the thing on the right. And now, this is still kind of overall from input to output just of an elbow. Now we can take this and scale it down another factor of 2, and then put it again at each one of the 8 vertices. Okay? And you can do it about 3 or 4 times, and then it gets too busy and don't see what's going on. And one of the nicest solutions was done by Jane Yan. She was one of the students in this class. And she also kind of colored it so it looks like red hot in the middle, and then it gets slightly cooler to the outside or so. So I then simply call this thing the Hilbert radiator pipe. And it's definitely cool, and that was the nicest result I got. But from a mathematician's point of view, yeah, this is not quite perfect yet. What did I didn't like? First of all, here there are 4 segments that lie in the same plane. Now, I would like, if we have 2 or maybe 3 segments in the plane, it's time to step in the 3rd dimension, okay? And so no planar segments in sequence more than 3. Also, it kind of breaks the symmetry. Obviously, there's kind of axial symmetry here, but then back down here, it doesn't work, and it's not even a closed loop, okay? So I was able to fix all of these flaws, and here then is again an Hilbert cube, so 3rd generation, and it's kind of almost, I have to be a little careful, it's a little wobbly because it only hangs together with 2 struts from left and right. I always think it's like a brain or something like that, okay? And the particular one that you see depicted here was also done by the X1 process that I mentioned before. So that's pretty cool as a sculpture, and they certainly liked it at SIGGRAPH in the year 2006. But a pure knot theoretist, he would kind of snarl at that. So that's not even a really interesting knot. I mean, it's just the unknot. It's just a loop. Nothing is knotted here at all. You know, so it's very complicated, wiggly unknot. Oh well. How can we fix that? Well, maybe we can fix it if the piece that we use to replace any one of the elbows by itself is actually knotted. So what about taking a little overhand knot and placing that one at each one of the elbows on our starting scheme? So something like that. We have an elbow and we replace this with sort of a Cubist knot version of this particular elbow. And to be consistent, we may actually start with sort of a Cubist trefoil, and then replace each one of these elbows with the shape I showed before, and here we get this. And now we have sort of a recursive Cubist trefoil knot. And that's really kind of what I was aiming for with this particular thing. Same approach applied to something like a Celtic knot. On the left you can see the recursion step. So Celtic knots show these over-under crossings, and I replace each one of these over-under crossings with this more complicated scheme, which has these 2 wiggles. And you can see in principle there's again still an input on top and an output at the bottom for red, and an input and an output for green on left and right. So we can simply put that at each one of these 9 crossing points, and we get this particular pattern. And this particular pattern still has kind of a red input on top and a red output at the bottom, and maybe a green input on the left and the green output on the right. So we can take this more complicated pattern and put it on each one of the original corners. To do that, I actually compressed it a little bit more. I just took the diagram before, I shoved it together so it's nice and compact, and then I put it at the 9 crossing points that we showed in the simple thing. It starts to look like that. Okay. And here is somewhat a different version of using such a recursive approach. Here I start by simply arranging 3 trefoils in such a way that they just touch each other's at these points. And then I make a switch over. I kind of go from blue to green, or from green to blue, and I make sure I use them in such a way, switching over, that the whole thing that results is still a single knot. And so if you trace it out, you can see, yes, it is one knot. It's not sort of like 3 loops hanging together. And so now I can take this shape and then put 3 of them together in the same manner, and again provide the same kind of crossover. And then I can do this once again. And here is sort of the 3rd generation of this particular approach. And yes, it is still a single knot. Here is sort of a view, oblique from a corner, close up to see what's going on. It's really kind of a 3-dimensional structure. And yes, we can put this on a 3D printer. And that's what it looks like when it comes out of a 3D printer. Underneath, of course, there's still that support that you cannot get rid of normally. Let's see. No, I need that yellow one there, the small one. Yeah. So just to tell you, 3D printers typically, you cannot just put plastic in midair and says, trust me, you will be supported eventually. No, you have to put this gray scaffolding underneath, and then you have to painstakingly kind of break it away. So 3D printers always need some way of supporting things. And so in this particular drawing, all that gray stuff underneath is kind of there to build it, but then once you break it away and clean it up freely, it really looks exactly like the thing that I wanted to show you. A third possible recursive approach focuses on meshes rather than on the actual crossings in a knot. And a stylized view of the figure-8 knot is drawn in such a way that the inner portion of it are simply a scaled down copy of the whole outer shape. Okay? So you can see this thing here, I can rotate and shrink down and put it inside. And then once more, shrink it down, put it inside. And so recursively, I can nest these shapes in one another. And in the end, I get this curve. And to now turn it into a knot, I simply have to go around and decide what to do at these various crossings. And again, I make it alternating, so over here, and then under there, over here, under there, and doing all that. And to make this process going quite a bit in depth and not just stop dead after 2 or 3 recursions, I also scale the diameter of this chord proportionally to the way that I reduce the shape to map it on the inside. Every turn essentially I map it down by another factor of 1.4, square root out of 2. And so this now essentially allows this process to go on ad infinitum. Robert Fathauer is another prominent member in the art and math community. He has used the same approach in this special view of a trefoil knot, which is shown in red. He rounded all the loops into perfect circles, and then it is easy to map the overall shape into all of the next smaller circles that you have. And this leads to a very pretty and decorative result. But it is somewhat flat, and at best it's kind of 2.5 dimensional. Now, can we use this approach and really get a truly 3D structure? And yes, we can. On the left is my original figure-8 knot design, which I consider to be flat. And then I make it more 3D by I turn the loop plane after every recursion step by 90 degrees and make sure it is always placing at the right angle to the previous 2 planes. And this makes a true 3D structure, and I can actually print this. And I think there's a model lying around here. And then I can mount this and photograph it cleverly so it looks like a really nice big sculpture. But of course it's still just a small model. And to conclude my talk, I would like now to give you a glimpse of what it really takes to make a large outdoor sculpture of a knot. The example I've chosen was conceived by Brent Collins. Brent Collins is an artist in Gower, Missouri, about 45 minutes north of Kansas City, with whom I've done several collaborative pieces. And here is the first sculpture that we actually worked together. But this is not a mathematical knot, but this one is. Brent had carved this 2-foot wood sculpture, and he explained to me his design thinking. To make it easier for me, I could then capture this shape in a computer program. As indicated on the right-hand side, the ribbon generally sweeps around a large outer sphere, but 3 times it dives inside the sphere and loops around 3 smaller inner spheres, indicated by those black lines. In this process, it forms, again, a topological trefoil knot. Now, this constellation of large and small spheres awakened an association that goes back to Ptolemy and Kepler, because they tried to explain the motion of the heavenly bodies by assuming that the planets were attached to crystal spheres rotating and moving of larger crystal spheres. Kepler also believed that the planets had their own individual musical melodies, which then all combined into one grand harmony. And so this led to the name of these sculptures, the music of the spheres. Then Brent got a commission to turn this sculpture into a larger outdoor bronze sculpture with a diameter of about 6 feet. And he asked help. Carlo, how can I do this? Well, first I made a small maquette generated by that computer program to emulate what he had done in wood. But we cannot just linearly scale this up. It would be much too clunky and too heavy and probably too expensive by today's copper prices. So we had to play with that model, and this, after some back and forth, essentially was the shape that we settled on. Note that the ribbon is much more slender, and again, it kind of narrows down as it goes towards the inside. I think overall this makes a much more elegant design. So when you then create the master geometry for something like that, you want to minimize the amount of milling that you have to do to define the starting geometry. Given that this sculpture had a threefold symmetry, 1/3 of the sculpture is really all that we need to define, and then we just make 3 copies. And you can see on the left, that's 1/3 of that particular sculpture. Of course, that piece, probably spanning the full 6 feet or something like that, is too big to be handled, definitely too big to fit into the kiln of Steve Reinmuth. So I had to break it down. 1/6 wasn't good enough, 1/9 wasn't good enough. The whole sculpture had to be broken down into 18 separate pieces, but that's 6 copies of 3 individual pieces shown here in different colors. I also provided some alignment studs shown kind of here to make it easier to then end-to-end put 2 of these pieces together by just clamping the alignment stud to make sure it's properly aligned, and then one of them also serves at the bottom to have the sculpture mounted on top of a pedestal. On an earlier sculpture I did with Brent Collins called Pax Mundi, I just focused on the geometry and I forgot about the physics. But at the scale that we do these things, the bronze ribbon is not totally stiff. Under the influence of gravity, the sculpture sagged by 15%, and that caused a real problem. Steve Reinmuth had to do a lot of fixing of all of that. So I was burnt, and I learned the hard way, and so used a tool that I could have used in the first place. And that tool, called Scan and Solve, essentially simulates and calculates how much a sculpture changes under the influence of gravity. And I ran that back, much too late, on Pax Mundi, and it tells me it sags by 15%. Red throws about a 15% displacement from where it was. So obviously I could have known. Well, I applied it to the new sculpture, and now the coloring is much more even. It says, well, the greenish stuff is maybe about a 3% change from the original position. So to me that would have been fine, but Steve Reinmuth was particularly careful, and he didn't want to have to do all the things he had to do to rescue the other sculpture. So he decided to only make the bottom parts solid, and then everything from about 1/3 up would be hollow, and save some copper and make things much more lightweight. And that means that many of these pieces, you had to have a much more complicated mold with a double wall. Okay? Well, he didn't realize how much trouble he's getting himself into it. Here's how the process starting. You start with kind of the master geometry that was milled based on my computer program on a 3D milling machine out of high density styrofoam. And then you kind of cover that, you give it a nice smooth surface, you put more and more silicon around it. And then with the silicon to get the fine structure, and with some extra struts and ribs and so on to hold the overall structure. That's what the final mold actually looks like. And here is another example of a complicated mold on the left, and then the kind of wax piece that you can now cast inside. And remember, in each one of these molds, we make 3 identical pieces. These pieces are then actually, in an investment casting process, turned into metal and then welded together. Here are a few more wax copies stacked up on the wall. You can see there are like 3 copies of that particular one. These wax pieces are then repeatedly dipped into plaster slurry, and it forms this thick shell. If you put them in a kiln, it hardens, and then that's how it looks after it has been baked in the kiln, and the ceramic essentially is now hard, and the wax has run out. Then you put this up, and you bring in your liquid bronze, and you pour it in on the end and filth of the inside. You wait until it's all cooled. Then you take it out in the backyard. The strong man with a sledgehammer knocks away the ceramic shell, and here's your sculpture. Well, not quite yet, right? First of all, you have to remove these sprues and runner, which were to bring in the bronze and distribute it nicely, and to also vent it and make sure the air can go out. And then you have to sort of clean everything up. And here are some more metal parts that just came back from the backyard. Here are the metal parts again, and you can see some of them have already been sort of cleaned, and the bronze starts to really shine. You can see how they're really sort of hollow on the inside. Okay, so much less weight than they would have been had it been all solid. And you wonder, what are all these holes of Swiss cheese there in this particular sculpture? Well, there was a problem, because this double-walled plaster, on the inside you also had this plaster, and it couldn't get rid of the moisture. And if you still have moisture in the plaster, you put that in the kiln, the whole thing flies in your face. So you have to wait until it's completely dry before you can put it in the kiln. But in here, there was just not enough ventilation to make this dry, not in 1 week, not in 2 weeks. And then Steve Reinmuth got very impatient, said, well, I have to put some vent holes in there. And he drilled all of these holes to allow the moisture to come out. And that was great. But it means that now in this stage, he has to go back and patch them all up again and put Bronzeville in there and then polish it all. So he made himself just a whole lot of more work. And so it's not surprising that, from the beginning, give us a sculpture until we had the sculpture, it takes about a year. But eventually you have the parts, and then you kind of start assembling. Here, they're like the first 2 that are, right at the bottom, starting from the support post. A few weeks later, the whole thing is almost complete. You see Steve Reinmuth here on the right. Not quite all the joints have been made. And then eventually, there it is ready for shipping, all welded together, and provided with this very nice kind of brownish golden patina. And here now is the installation at Missouri Western State University in front of their science center. Here the crate has just been opened, Steve Reinmuth again. Here it's carefully positioned onto the stainless steel pedestal. Final moments of installation, and on the right, 2 very happy campers, because this sculpture really looks great. And at night, when it's properly illuminated, it looks even more spectacular. So, you may wonder, is this math or is this art? And this reminds me of a joke by Mike Tuhai, where the artist states, I don't say my work is art. That is for others to decide. And Joe Sixpack answers, it is not art. And I say, it is not art. Thank you for your attention. Questions? Yes.
Has anyone tried to make music out of your music sculpture? Like, I think you could project the individual planes onto a snap.
That's an interesting idea. Nobody has done that to my sculptures, but there are some very famous movies. There's a process where mathematicians show how to turn a sphere inside out. Okay? Now, you have to allow a surface to pass through itself, but you cannot make sharp creases or anything like that. And then John Sullivan has made a beautiful movie that shows that whole process. And anytime something interesting happens topologically, like if 2 surface fronts come together and touch it, it goes boing. And then, if 2 curves kind of cross one another, it goes bling. And so there's a music that goes with it, which is generated by the topological events of turning a sphere inside out. So you're quite right. I mean, mathematics and music has very close relationships, and some people have actually linked geometry and music in some way, but not as far as I know anything done with knots yet. Yes?
Two questions. A while back, you were dealing with, I think, red and green, and you would show the green coming in and the green going out, and then the red coming in and the red
Those Celtic knots, right? Yeah.
But was that actually two separate strings, or was it one somehow tied back together?
Okay. In this particular case, it has not been wired up to form one particular loop. So, as red and green, as I look at this local perspective, they're truly two separate loops. Now, many of the Celtic knots are actually not a single knot. Some of them are actually multiple loops. It all depends when you drape it around, so the frame of a window or something like that, what you want to do. And so in order to close it, all of the pictures I had, they were kind of open-ended. They had always one red going on top and bottom, one green left and right. And so it would depend how you take multiple of these panels and in the overall scheme kind of lock them up, whether you connect them all into one loop or into multiple loops.
Second question.
Yeah.
And again, maybe it's probably just me. What does this have to do with math?
This is math. I'm running for 22 years the annual Art Mathematics Bridges Conference, and it really shows the connection between math and many other cultural ventures, because there is math in everything, obviously in sculpture and in painting and in music and in dance and in juggling and in macrame and in origami. I mean, math is just penetrating, and clearly there's a lot of math in knots. Actually, knot theory is a wonderful little subfield of mathematics that people can get into without having to learn all the hard mathematics. You don't have to know about tensors and linear operators and God knows what. You can read one book, the Knot book by Alan Holden, and you don't even have to read more than the first 50 pages, and you can go and be creative and do something. And so we find many kind of, I would say, non-mathematicians that also venture into knot theory and do great stuff. Okay. Now, the other thing we do at the Bridges Conference, we always have a family day. On our family day, we bring out puzzles and things the student can assemble and all kind of fun-looking stuff. And these children, anywhere from age 4 through teenagers, they play and they have a great time. And when they're really, really happy, we tell them, that is mathematics. And so now mathematics gets a much better, kind of image than if they go through middle school, they have to rote learn all the multiplication tables, and then somebody claims this is mathematics. No, no, give me a break. Mathematics is much more interesting and deeper than multiplication tables. Yes?
Well, you can graph an equation on a Euclidean plane,
Yeah.
XY axis, and you can have various curves and loops from one equation.
Yeah.
Graphing an equation.
Yeah.
You graph a three-dimensional equation on three-dimensional planes, and
Right.
you get three-dimensional loops. And so that's what you're talking about. But you don't actually go and write out an equation to make your sculptures, do you?
No. People often ask me that, what is the equation for one of these things? And I don't know, okay? Because I'm not trying to find a formula that by having one parameter, say time, and simply for every time point gives me all of those points and so on. No, that's no fun, and it would be very complicated. I do really a much more constructive approach exactly the way it is. So typically, I would take one generic piece, and there are some curves that you typically find on any kind of graphic editing tool, be a B-spline or a Bezier curve, and with a few clicks, you make a control polygon, and then the computer makes a nice curve that kind of roughly follows that, makes it nice and smooth. Knowing what the symmetry is of that, I only need to make this piece once. And I know I get exactly that same piece again, rotated 180 degrees. So in my program, I make one of these little simple curves and says, okay, put one here, put one over there, put one down here, put one down there. And then I have the math in such a way that they really line up. And so I never see one equation for the whole thing. I just see these individual pieces of little worms stuck together the right way until I like it. And I have no idea what underneath the math really says because it's all done interactively on the screen. When I like it, I save it as a so-called STL file, which breaks up that surface in tiny little triangles, maybe 100,000 triangles. Send that to a 3D printer. And they know what to do.
That just proves that you are an artist based in math.
Yeah, I think it's exactly that. I'm just straddling that gap, you know. And it goes both ways. So with Brent Collins, I get inspired by some of his work, or by Hillman Ferguson and so on, and I try to see what is going on, what's the underlying structure, and then write a computer program to capture that particular shape. But having a computer program, I can now easily change it. I change some parameters from 3 to 4, and it changes the shape ever so slightly. Or I run something not 3 times around, but 5 times around, or 7 times around. Okay? On the other hand, sometimes I may start with trying to make a mathematical model to explain what's a Mobius band, or what's a Klein bottle, or what's a genus 5 surface, or something like that. And I try to make them nice and attractive. And sometimes they're so attractive that they could stand there and people would love it, not having the least clue what the math is behind it and why there should be any math, right? So it's really going from math to art, or from art to math, both ways just as easily. Yes?
Think about adding the fourth dimension of time, and what would it look like?
Oh, I thought that was too much, so I didn't bring that one. But good question, because that's what I'm working on right now. So, in the fourth dimension, how about the fourth dimension? All right. In 3 dimensions, we have the 3 Platonic solids: tetrahedron, octahedron, the cube, icosahedron, and dodecahedron. I've seen 4 of them you have seen here tonight and all of that. Turns out the fully regular objects in 4 dimensions, there are 6 of them. Okay? And the simplest one is the so-called 5-cell. Just like a tetrahedron is made from 4 triangles, the 5-cell is basically made by assembling 5 tetrahedra as of a thick crust in 4 dimensions. The simplest graph to show that would be a tetrahedron with 1 more vertex in the middle, and connected to all 4 vertices. The nice thing that this particular graph has 5 vertices, the 4 original tetrahedron vertices and 1 in the middle, and all the vertices are already valence 4. So making an Euler path on that little object is trivial. I don't have to duplicate any edges or something like that. So I did just that. I essentially run an Euler path, and then at each vertex I just loop them around once each other. And I'm in the process of doing the same thing for a hypercube. Now the hypercube is like a big cube with a smaller cube inside, and then diagonal struts connecting the two. And again, the cube had valence 3 vertices, but because of the extra strut that goes from the small cube to the bigger cube, all the vertices are valence 4, and so I can readily do an Euler path on it. Problem is, can I make sure that this is not multiple loops, but 1 single loop, and at the same time have as much symmetry as possible? And just like the example I showed between the green and the yellow sculpture, I can either have maximal symmetry, but then it's probably more than 1 loop. Or, I can force it to be 1 loop, but then I break some of the symmetry. And that's what I'm sort of struggling with. And maybe next time I give a talk, I have a result on that. Yes, please.
In addition to this knot art application, does it have any other, with all the knots, is there any way you can use this for, I don't know, building?
Yeah, I mean,
other applications?
that's the tough question. People always come and says, what is this useful for?
Yeah.
And I really don't have a good idea, okay. But often, mathematical concepts, they get invented, and then, maybe 100 years later, somebody kind of, makes something useful out of it. So like Minkowski spaces was a completely abstract kind of thing, and then Einstein figured out, oh my God, that's exactly what I need to explain, special relativity. So I'm not sure to what degree knots have kind of triggered interesting things. Knots themselves are sort of interesting. About 20 years ago, chemists tried to make knotted molecules. And they very carefully tried to construct things with bridges and so on that they then removed the studs between them, and then ended up with actually a little molecule that was like a Trefoil knot, or maybe a figure-8 knot, and big success. Well, in the meantime, we have figured out that many of the DNA strands or proteins sometimes actually are really knotted, okay? And so nature has been doing that on a much more complicated scale, long before, we chemists have sort of followed up on that one. So nature knows about knots, okay? Is it useful? I don't know. Nobody kind of knows whether those knotted things have any extra properties that would make it better to read off the information or not.
So please join me in thanking Professor.
Thank you. Oh,
I actually do think.
arts and sailing, but nothing of interest for a knot theoretician because it's not closed loops.
Well, I was a math major, but I think I got discouraged by lack of application.
Thank you. And also,
Save the world,
I think in most mathematics courses, knots are not something that's being treated because it's kind of its own little field, and then what you do with it. But I'm teaching essentially graduate courses on computer-aided design, on rapid prototyping, and basically on symmetry and the like. And there, of course, knots were wonderful, right?
Yeah. Thank you.
You're welcome.